trajectory simulator and was developed by 2 UKZ graduate students. Bernard Genevieve has designed the MATLAB-based hybrid rocket performance code, and Sefa Chowdhury has developed the C++ code of 6 degree of freedom flight dynamics model. These models form the basis of HIROPS. The model has been an essential tool for the development of the optimization of the Phoenix 1A, along with CFD and FEAs to ensure structural integrity, and has also been used for the preliminary design of the Phoenix 2A. The Phoenix 1A uses medical-grade nitrous oxide as the oxidizer, which has been helium supercharged to a working pressure of 65 bars, and Sasol 0907 paraffin wax as the fuel. The nitrous oxide will be delivered to the combustion chamber via a blowdown process. This is to reduce complexity and cost. However, the oxidizer mass flow rate can be throttled by the actuation of the delivery valve by a high-torque servo motor. The cross-sectional view here of the Phoenix 1A indicates the positions of the flight computer's recovery system, oxidizer tank, feed system, and combustion chamber. The vehicle airframe structure has been designed around the PB1 flight motor and consists of a bow tail, 4 stabilizing fins, a tapered fairing, the recovery system and flight computer bay, and a nose cone. A dual parachute recovery system with a nominal splashdown velocity of 5 meters per second will be employed to allow for full land or sea recovery. The airframe is also designed for supersonic flight. The PV1 flight motor parameters were obtained using HIROPS for an optimal apogee. The motor comprises of a injector, dual igniters, an injector bulkhead, an aluminium combustion chamber casing, a paraffin wax fuel grain, a graphite nozzle, a nozzle retainer, a carbon phenolic thermal liner, and a pre- and post-combustion chamber inserts. The injector bulkhead can accommodate alternative injector, igniter, and pressure transducer fittings. The PV1 motor and Phoenix 1A airframe have been designed, and procurement and manufacturing of these components is currently underway. The inaugural launch of this vehicle is scheduled for early next year, over the sea from Denel Overberg Test Range, which is located at the southern tip of, near the southern tip of Africa. The Phoenix 1A will be launched from a purpose-built mobile launch platform, which has been designed by an undergraduate team. To improve resource utilization, it has also been designed to be the static flight motor test stand. The mobile launch platform has an adjustable gantry, allowing for a 60 to 90 degree launch angle range, and accommodates all the ground support equipment that are required for launch operations. The nitrous oxide and helium supercharge are independently loaded into the oxidizer tank via a bidirectional quick connect valve. This valve allows for emergency venting during filling and testing. The connect valve can be disengaged by a pneumatic linear actuator and is a self-locking mechanism. For safety, the filling procedure is fully automated and controlled by a lab view program. Here are some photographs showing the components that have been manufactured so far. The Phoenix 2A is the second vehicle of the program and is designed to deliver a 5 kg payload to at least 100 kilometers in altitude. The vehicle will use nitrous oxide, but unlike Phoenix 1A, it will use a 40% aluminized paraffin wax fuel. The additional aluminium was used for the design, as it has a number of advantages, such as improved specific impulse and increased overall propellant density. The addition of aluminium allows the design to have a lower oxidizer to fuel ratio. This means that less fuel is required for a specific amount of oxidizer. It also increases the regression rate coefficient by a factor of 10%. The basic preliminary design has been performed using the HIROPS and will be used as a baseline for further parameter optimization and structural work design. As a starting point, data associated with Peregrine, a 100-kilometer sounding rocket developed by Stanford University and NASA Ames, will be used to provide initial approximate target values. So together with Peregrine's total impulse and the Phoenix 2A's burn time, a conservative design thrust value of 50 kilonewtons was selected. The vehicle was also designed assuming 95% combustion efficiency. The higher-ups code was used to model the motor performance using the input shown on the table on the right, left. Then the table on the right shows the outputs generated by the code. The code uses theoretical rocket performance data that was obtained using NASA CEA, which is integrated into the code, and the equations on the slide were used to calculate these outputs. With all this information, the grain dimensions could be determined. A pressure regulating system was used for the preliminary design as it improves the performance, but it reduces the reliability and increases cost. A simplified airframe was designed around the grain dimensions. The wall thicknesses of the oxidizer tank and combustion chamber were determined to give a safety factor of 1.9 based on the predicted hoop stresses. The pressures used were 1.5 times that of the expected operating pressure. To enable trajectory analysis, the airframe model was modeled in higher-ups using a combination of standard geometries as shown. For example, an ogive for the nose cone, an annulus for the combustion chamber, and a truncated cone for the tapered fairings. The tapers were kept to an angle of less than 8 degrees to limit flow separation effects. Propellant consumption during the burn-up time was also simulated to provide a time-varying weight distribution. The vehicle was designed with fins that were canted by half a degree to provide a spin rate of approximately 2.7 Hz. Aerodynamic coefficients were obtained using RAS Aero, which is an aerodynamic analysis software package, and these were then imported into higher-ups. The Phoenix 2A was simulated for an 80-degree launch angle and no wind effects. The variation of thrust with altitude is captured by the higher-ups code to correctly model the motor performance and therefore trajectory of the vehicle. The video demonstrated the Phoenix 2A's trajectory for a launch angle of 75, 80 and 85 degrees. The Phoenix 2A's preliminary design is predicted to achieve an apogee of 117 kilometers in approximately 170 seconds. The vehicle is 9 meters in length with a launch and burnout mass of approximately 786 kgs and 389 kgs respectively. The mass of minor items, such as the oxidizer feed system and flight computers, have been neglected due to the simplified nature of this design. A mass change may occur after a detailed loading analysis has been performed on all the components. The graph on the right indicates that the thrust is slightly higher than the design thrust of 50 kilonewtons. This is predominantly due to the fall in ambient static pressure with regards to increased altitude. The maximum acceleration that the vehicle will experience is approximately 12.6 Gs. This is acceptable for the preliminary design. However, the inertial loading sensitivity of the vehicle's payload will dictate what the maximum allowable acceleration can be. The thermal conditions of the vehicle thermal protection must also be considered because, especially where the stagnation conditions occur because of the supersonic Mach numbers that the vehicle achieves. Future work include the optimization of the Phoenix 2A's structural and aerodynamic efficiency using an iterative process. CFD and FEAs will also be performed to ensure structural integrity. The optimal expansion ratio will also be determined for the best apogee. Darting of the vehicle will be investigated as the burnout altitude for the vehicle is 11.95 kilometers.